Welcome back, physical science class. We're going to talk about module 16. And module 16 is basically the module of everything. It's the module of the universe. And obviously it's not going to cover the universe in a huge amount of depth, but it is going to cover a lot about space, a lot about light in our solar system, really stars in particular. So we're going to begin by talking about the sun. So there are billions and billions and billions of suns, of stars in the universe. But ours is kind of unique in a few ways. Number one, out of the type of star that it is, it's unusually large. Another thing is that it's actually unique, believe it or not, in existing by itself. Turns out that most solar systems are going to be multiple star systems, meaning that there's one or more, or two or more stars in the system. So imagine you got what we have, which is, of course, the sun, and we got, like, you know, Mercury, Venus, Earth, Mars, etc., orbiting around that one sun. And of course these paths are elliptical, and I'm not drawing all of the planets, but you get the idea. And is that showing up well enough? Might need a darker marker. Maybe that'll work. This is a dark green, so my blacks are running out of ink from overuse. Now, imagine, instead of having this kind of uniform orbit, which is slightly elliptical but not really that different around the year, imagine that you have two stars instead, and they are interacting with each other, and then our orbits, you know, our planet's orbits are no longer just this nice normal path. Now they're going to be kind of compensating for the differences in the locations of the stars relative to each other. And basically, if you have a two or more star system, then your planet's going to have certain times of the year when it's really, really, really hot, or really, really, really cold in comparison. So basically, it's definitely important that we are in a one-star system, not a multiple star system. Other things that are interesting about the sun and unique about it, specifically, you know, I would say providential about it, like, you know, absolutely necessary for sustaining life. It turns out that it's just the right size for supporting life on Earth. And I mentioned that it was large for its type. Its diameter is about 100 times that of Earth's. And you could actually fit 1 million Earths inside the sun. And so specifically, the sun is 865,000 miles in diameter. That's pretty big. And its mass is about 330 million times that of Earth. And that's actually interesting because it's not made of heavy stuff. The sun consists of 74% hydrogen, 25% helium, and of course these are like approximations, and then about 1% other stuff. Now, how is it that it's so heavy if it contains very light gases? This is something with only one proton, this is something with two protons, very light gases. And think about how hydrogen and helium, they actually, like, you know, helium balloons will float upward because they're lighter than the rest of the air around them. So it's because of the gravity of the sun. So there's so much matter. The way a star forms, interestingly enough, is just the result of a huge amount of matter and a lot of time with gravity. So a star is formed, this isn't in the module by the way, but you have a nebula, which nebula literally is just Latin for cloud, if I remember correctly. And so all of this hydrogen gas just kind of floating around in space. And where there's a huge pocket of it, eventually the little bit of mass in all of that hydrogen will attract other hydrogen. And so over a vast amount of time, you end up with the hydrogen all traveling inward, and that inward gravitational force It's going to get stronger and stronger the more hydrogen is collected. And since in these nebulae, which is the plural of nebula, first declension Latin word, since the amount of it is so much, you end up with just vast, vast amounts of it packed in, and it starts to spin also. And as it does, it's kind of cool. It makes like a disc, and then light and heat will shoot out for light years from the center, and just covering huge distances, and almost like turning on a lightsaber on both sides or something like that, but on a cosmic scale. And so this swirling ball of gas eventually compresses and compresses, and the gravity intensifies and intensifies until you end up with a star, where it's all compacted into a nice little tight ball, or roughly spherical object. And at the core of the sun, or any star, is where the gravity is going to be most concentrated and everything is going to be the most dense. So we'll talk about the different regions of the sun real fast. And I think maybe I'll switch to a purple marker, or I'll try a blue one, see if that shows up. Nah, purple. The purple's real dark. So here are the parts of the sun. You've got the core. Yeah, that shows up real well. Then we have a great big radiative zone. Outside of that, we have a convection zone. And then right at the top, the part that we see, the surface of the sun, is called the photosphere. So think photon. So how is the sun powered, basically? It's interesting to note that at any given moment you have enormous forces bringing the sun in and tearing the sun apart. So the force bringing it in is the gravity, and that's keeping all the explosions and reactions in the sun at bay. But then you also have these huge explosions on especially the surface of the sun that we see. And the most powerful ones are going to be called solar flares. Those are much more powerful than the normal ones, and those will happen every now and then and disrupt satellites and power grids and radio communication. They're not the best thing for us, and they would cause damage to Earth except for our electromagnetic field. Anyway, so all these explosions occurring, all these reactions occurring, they're kind of held at bay by gravity. So the sun's not just like supernovaing and exploding everywhere. And at the core, there's enough heat and pressure that a reaction called fusion can take place. So when fusion occurs, you have basically just a bare proton, which is going to be hydrogen 1 without its electron. And then we're going to have a proton and a neutron with no electron. And this is going to be hydrogen 2 stripped of its electron. And why do they not have electrons? It's because of the conditions in the core. It's got so much pressure and so much heat that the electrons are actually going to be stripped off of these atoms. And so when these two collide, and remember with heat, you actually have just like, you're adding motional energy to the matter. That's what heat basically is. It's going to be vibrations, and in this case, like, bouncing around and going everywhere. So there's a lot of bouncing and a lot of collisions, and when hydrogen 1 and hydrogen 2, without their electrons, strike each other in the right way, then they'll fuse together, and they'll create a helium-3. They'll fuse into a helium-3. So helium is your element when you have 2 protons and then a neutron. And I guess even the helium-3 wouldn't have, it doesn't have any electrons. And when it does that, some energy is also released. You can see this on figure 16.1. 16.2. So fusion That says energy over there, by the way. It's getting cut off a little bit. Fusion is the most powerful way we know to release energy. There's other reactions, for example, fission, and fission is different. What happens with fission, and this would be visible on figure 16.3, with fission, you have, let me skip ahead, this actually appears later in the module, basically a really large, here's nuclear fusion, and then here is nuclear fission. In the case of nuclear fission, what you're doing is you're splitting an atom rather than combining like in fusion. So in that one, you got a neutron, which is energized, and it's going to strike an especially large nucleus. I'm just going to kind of draw it like this, but it's a very large nucleus. And when it strikes it, it's going to split it into two smaller nuclei and also release free neutrons. So then there will be some neutrons bouncing around, and you can't really see them over there, so I'm going to draw some neutrons in this direction too. Now, a nuclear power plant, what they do is they take a whole bunch of these nuclear, like really large atoms. Basically, it's going to be some kind of an isotope that is really big and rather unstable. And then they accelerate neutrons into it. And what happens is a chain reaction. Because if you have a lot of this type of unstable nucleus close by, like right next to each other, packed in, then when one of them splits and then it releases these neutrons, which will start other ones, it's like when you take, when you're playing pool and you take that first shot, except imagine that every single one of those pool balls, like billiard balls that you strike with the cue ball, is going to generate 3 or 4 or 5 or something, you know, more little billiard balls that are then going to strike other billiard balls, which are going to generate 3 or 4 or 5 or whatever more. And as it happens, energy is released each time, and it's basically just this accelerating chain reaction. So that's what happens in nuclear fission. You split an atom, and it releases more of those energized neutrons that can split more atoms. And as I mentioned before, what's happening in the nucleus of an atom is you have two forces. You've got the nuclear force, which is a manifestation of the strong force, which exists only over a very small space, holding these protons together, which are actually repelling each other very strongly under the electromagnetic force, because it's two positives being crammed together when you have 2 or more protons in a small space. So you're busting open, you know, you're basically breaking open the atom, and then those protons can finally be free and shoot away from each other, and that releases a lot of energy. And if you have a big chain reaction, you can go from something like a nuclear power plant, which is more controlled, to if you have like enough of this stuff that it creates this big chain reaction, then aka a critical mass of your radioactive isotope, then it can actually result in like a nuclear bomb or something. So anyway, that's a comparison between nuclear fusion and nuclear fission. I'll also point out with nuclear fission a few things. Number one, fusion will produce more energy. And also, nuclear fusion will produce more energy, and you can fuel it with just water. So, because you just need hydrogen, and so you can just extract the hydrogen from water and use that to fuel it, whereas with this you need relatively, you know, comparatively, compared to water for sure, rare isotopes to get this going. So you have a more expensive fuel with this one than with this one. Less energy is released with this one than with this one. And then in terms of waste or byproduct, this one releases radioactive chemicals like waste, basically radioactive waste that takes very long periods of time to become safe. So you create pollution that's a real problem with nuclear fission, although, you know, arguably it's easier to contain, and, you know, if you contain it well, then it's not as bad as other, it's cleaner than other energy sources. But then with nuclear fusion, you're not creating any really bad byproducts, or at least not enough. So all around, this is much better. So the question is, why do we have nuclear power plants that use fission but not that use fusion? It's because if you're going to create fusion, you need the right conditions, and you find them in the sun, where there's a gravity well that's so much greater than anything we can create on Earth. And so it's pretty hard to create fusion. In fact, fusion, even in the sun, is only going to occur in the core, where you have the most heat and you have the most pressure. Now, we have actually created in laboratories fusion reactions. So we can do fusion here on Earth. The problem is it actually costs more to do fusion than you would gain by selling the energy released. So in other words, it's just not worth it yet. Maybe someday it will be, but it's not yet. All right, so we went over kind of two sections in one there. I skipped ahead and discussed nuclear fission versus nuclear fusion. And remember that fusion is going to occur in the core of the sun, in that intense heat and pressure. In fact, just so you know, the core is 27 million degrees Fahrenheit. And as far as the amount of energy that's released, even from a small reaction under fusion, by the way, I mentioned this in last module's video. I think it was last one, maybe 2 videos ago, but last module. Einstein's theory of general relativity, you have the E equals mc squared. Sorry, special theory of relativity, his special theory of relativity, E equals mc squared. And that means energy equals, equals mass times c is actually the speed of light, which, as we discussed last module, is very, very fast. They reiterate that in this module, squared. So if you have matter, then you multiply it by the speed of light squared, and that's how much energy you're actually releasing from that matter if you were to convert that matter into pure energy. So you take tiny amounts of matter and convert some of it into energy, and not all of it, but just some of it, when you have a fusion reaction, and it releases tons and tons and tons of energy. In fact, it says that if you took a gram, which is very small, of matter and converted it into pure energy, then according to this E equals mc squared formula, guess how much energy would be released from a single gram of matter? It would actually be enough energy to power a 100-watt light bulb for 28,500 years. Now, when fusion is occurring in the core and releasing those vast amounts of energy, what happens is some of that energy is going to be heat energy that heats the core. Some of it's going to be, and actually the majority of it is going to be converted into electromagnetic waves, basically photons that are going to work their way out of the core, and they're bouncing around in the core, and they'll actually work their way up into the radiative zone. And in the radiative zone, the photons are going to bounce around for a very long time, and there's the gases that are tightly packed in here, but not as tightly as in the core. They are going to, again, not support fusion because they're not dense or hot enough. Anyway, they're just going to kind of be a zone where the light from the fusion reaction in the core has to get through all these gases and work its way up. Then in the convection zone, this is where photons are typically absorbed by gases and heat up the gases. So here, the photons get a lot of them get absorbed in the gases, and so then the hot gases in the convection zone at the, as they heat up at the bottom, they're going to rise to the top and then carry that heat up into the photosphere, which is the surface of the sun again. And then as they cool down, because they've transferred the heat to the photosphere, they're going to descend back down and kind of cycle, heat up, cool down, and cycle back and forth from the top to the bottom. But they're transferring energy to the photosphere, which is where you're going to see all the light actually escape and radiate outward through the solar system and beyond. and you know, all those eruptions and solar flares, etc., are going to occur there. So when we get to the photosphere, um, you're going to have photons emitting light from almost the entire electromagnetic spectrum that we talked about. So you're going to have visible light, UV light, X-rays, gamma rays, all radiating out of the sun. Now it's interesting, they didn't mention infrared light, but I'm pretty sure infrared is in there. I haven't looked it up, but you can look it up. Because we talked about with the greenhouse effect, like infrared light from the sun gets trapped in the earth due to the greenhouse gases. So anyway, yeah, I think that was probably just an oversight that they didn't mention infrared light. That's my guess anyway. Unless somehow I misunderstood greenhouse gases, but I don't think I did there. So we're going to move on to another section now. We're going to talk a little bit about classifying the different stars in the universe. So stars can be classified according to temperature. And a couple of manifestations of temperature that we see are going to be the color and the brightness of the star. Now, there's a process called spectroscopy. That scientists use to determine basically the temperature of the star by looking at the individual wavelengths of light that come from it. And so it turns out that just as on the visible spectrum, on the one side you've got red, remember Roy G. Biv, and on the other side violet, so red, orange, yellow, green, blue, indigo, and violet. Now, which one has the most energy? That's going to be violet. So this is going to be the highest energy side, because it's the side with the highest frequency. And then the R is going to be the lowest energy side. And remember, heat is a form of energy. Oh, it turns out actually, I did research whether or not the sun emits infrared light, and yes, it definitely does. So that was just an oversight in the book that they didn't mention that one. So anyway, it turns out then that the coolest stars, are going to be red-orange stars. And then you have yellow stars, which are going to be a little bit hotter. Then you have, actually in between, I'm just going to add it up here, you have white stars, which are, I'm just going to label that as white, hotter. Then you have blue stars, which are going to be the hottest. So stars can come in all kinds of different colors, but what you're generally going to see is the red-orange ones, which are the coolest. You're going to see yellow ones, which are a little hotter. You're going to see white ones, which are a little hotter, and that's actually the type that our sun is. And then the hottest ones are going to be blue stars. There's a couple of terms for the brightness of a star, which we can go over. And again, the brighter the star, the hotter it is. Now that, of course, is only true if you account for the distance of the star. So for example, what's the brightest star for us here on Earth? Obviously the sun. In fact, it's so bright that in the day we don't see any other stars at all. However, if you were to account for distance, then ours is a relatively bright star, but not anywhere near the brightest. When dealing with the brightness of the star, there's two terms. There's the absolute magnitude of the star, which is a measure that's going to range from a scale of -8 to 19, with -8 being the brightest and 19 being the dimmest, or dullest, however you want to say that. And absolute magnitude is going to be the real brightness of the star if you're accounting for distance. So it's like if you were equidistant from every star and measure the brightness when you had an objective reference point like the same distance from every single one. Then we have the apparent magnitude, and they don't actually give you a stretch of measures for this one because probably, my guess, would be because your reference point would change that so much. Like, to give you an idea, this is going to measure just how bright the star appears to you. And for us, the sun would appear to be a measure of -27. But if we were to all of a sudden travel through space and be right, an Earth distance away from a much brighter star, then it would be a far lower number than -27. And classifying stars based on brightness and color, and using spectroscopy, we can discern basically how hot all of the different stars are that we feel like cataloging. And from there, we can actually assign a number, a letter to each of the stars to classify them. So from coldest to hottest, and I'm going to do it this way. I'm actually going to go from coldest to hottest. Let me consult the book here because they actually have this in reverse order on this diagram from the way it was written before. So here. You know what? I think I'm actually going to copy it exactly. I was thinking these lines might be useful, but they're not in the book, so I'm not going to do it. So these letters right here are representing the heat of stars. So the hottest stars you're going to classify with the letter M, followed by a K, G, F, A, B, and then O is going to be the coldest. And also we can use the absolute magnitude of stars. So this is going to be going to the brightest. So the hottest and brightest stars are going to be up in this corner. So -10, -5, 0, 5, 10, 15. So this diagram is a chart where they've just charted a whole bunch of different stars and classified them. It's got an interesting name. It's called the Hertzsprung. Russell diagram. They also call it just the HR diagram. And so in charting these stars, what we kind of found is most stars are going to go in this diagonal pattern. It's not like a perfect diagonal, it's got some bends to it. And this section is called the main sequence. It's where 90%, I'm sorry, is it 90%? I think it might be another number. Give me just a moment. No, it is. Yeah, about 90% of stars are main sequence stars. And you may notice that they have a pretty linear relationship, or linear correlation, um, between the, or you could say they're directly proportional, is another way of saying it, between the brightness and the heat of the star. So basically, the hotter the star, the brighter it is if it's a main sequence star. Then there are little pockets of stars that are different from that. Like there's a cluster way down here of white dwarf stars. I don't know why it's dwarfs and not dwarves. That seems weird, but whatever. And so the white dwarfs are going to be a little different. They're very hot, but they're not very bright. And that may have to do with the fact that they're small. They're actually really compact. A teaspoon of white dwarf star material would weigh tons on the Earth. Literally tons. Then up here, above the main sequence, you got a pocket of red giants, dwarves and giants. And red giants are going to have cores of mostly helium, and they do undergo fusion, but it's not fusing hydrogen into helium, it's fusing helium into carbon, interestingly enough. And so their cores are hotter than main sequence star cores, but on average they are not as hot of stars as main sequence stars, and that may have to do with the fact that they're really, really huge. So then, like, you know, the outer portions could be farther away from the cores, which are hot. So then we have a cluster of supergiants, which are pretty hot, but they're very bright. And so supergiants are actually extremely rare. And the sun, by the way, is somewhere around here on the main sequence. So the sun is a main sequence star. It's a rather unique main sequence star, and I'll let you read the book to find out more about why. So we're going to move on to another section, and I'm not going to hit this section in very much detail right now. I can cover that in the next video. And in this next section, we're going to be talking about variable stars, quite briefly. Now, variable stars are going to be stars, excuse me, I'm sorry, just a moment, that don't actually have a constant magnitude. So in other words, sometimes they'll be brighter than at other times. And there's a couple of different types of variable stars. And so one of them is pulsating variables. The other one is novas. Now, novas are actually going to be stars that are kind of like exploding. And a star can explode lots of times without going out. And it's called nova, which is Latin for new, because early astronomers would see this flash of light and think that a new star had been born, but it was really an existing star that was just erupting. But if a star goes supernova, then that's the end of the star. That's when it fully explodes. So obviously, if it's undergoing like large-scale explosions, then it's going to be having a variable magnitude. They actually have discovered the Crab Nebula is probably the result of a supernova that was charted actually in, you know, recorded history in the year 1054 AD. Now, we're going to talk a little bit about the pulsating binaries, or variables. Pulsating variables are going to be stars that actually expand and contract. There's a certain subclass of them called Cepheid variables. So the Cepheid variable class of stars. And these are really large. They're like 20 times as massive as the sun. And so they have a constant rate of expanding and contracting. And so as a result, we can actually use them to measure the length of the universe. They're really helpful with that process. So there's also going to be different things like that are just kind of interesting types of stars to point out, like binary stars. These are going to be stars that are very close to each other, so they're like in the same solar system. But then we also have eclipsing binary stars. Just going to hit these really fast, all this stuff, all these different types. You can read about these. They vary in apparent brightness, not because their absolute magnitude changes, but because one of the stars can block the view of the other. So imagine, like, you know, the absolute magnitude of eclipsing binary stars doesn't change. It's just that one of them will eclipse, meaning block the other one, and so then you don't see its full light. So its apparent magnitude is what's variable, not its absolute magnitude. Now we're going to talk a little bit about measuring the distance to different stars. So there are two actual ways to measure the distance of a star. The first one is called the parallax method, and I'm going to go into that in my next video, and I'll just write it on the board though. Oops. There goes my marker. So, parallax method. It's going to have to do with actually triangulating a star and measuring using an angle its distance. But for longer range stars, there is the apparent magnitude method. I'm not going to go into much detail about this one, but basically, I mentioned that Cepheid stars, the variable class, Cepheid variables, they pulse from being brighter to dimmer to brighter to dimmer, and it was discovered that the period that it takes to go from bright to dim, from the brightest to the dimmest, if it takes a long period for the star to transition, that's actually going to mean that it's going to have a greater magnitude. Or as in well, it's going to have a lower number of magnitude, a negative number, perhaps, but it's going to be brighter star because the magnitude is actually measured with positive being low brightness and negative being high brightness. So scientists have been able to use that principle in order to measure the magnitude and distance of stars. So you can read about that in more detail. There is a concept we can go over real quickly. It's a vocabulary word that I'm sure you've already encountered in your life and probably know pretty well. A galaxy. And so a galaxy is a large ensemble of stars. So big grouping of stars, all interacting through the gravitational force and orbiting around a common center. So I'll just say orbiting around a common center. So our Milky Way galaxy is actually this huge, huge, huge sea of stars. They're all orbiting around the same central point. There are different types of galaxies. There are elliptical, lenticular, and irregular. So, or I'm sorry, spiral, elliptical, lenticular, and then you can just have like an irregular. So spiral, lenticular, and elliptical. So it's good to know that there are those three. And so ours is actually ours is going to be a spiral galaxy. A lenticular galaxy is going to look similar, but without the arms. It's a flat disk with no spiral arms, and then an elliptical galaxy is just going to be a flat disk, but more globular than the lenticular. So you can see those in figure 16.7, get a better idea of what they look like. I'm not going to take the time to draw a picture. And then the last would just be if it's not any of those, it'll be an irregular galaxy. Now, it turns out that the universe is expanding, and one of the ways that we know that is because of the Doppler effect. So there's something going on called the red shift. And the red shift think about in the case of an ambulance coming toward you, remember how in the Doppler effect, the ambulance coming toward you, its siren is going to produce a higher and higher pitch as it comes toward you because the sound waves are going in the same direction the ambulance is traveling. So the ambulance is catching up to its own sound waves. They're getting bunched up, creating shorter wavelengths, which means a higher frequency, which means a higher pitch sound. And then if the ambulance passes you, as it's traveling away from you, it's outrunning its own sound waves. Not that it's going above Mach 1, but just that it's moving in the opposite direction. So as it's generating the sound waves are getting farther and farther apart as it's leaving a trail of sound waves behind it going the opposite direction. So it becomes lower pitch. What would happen if the Doppler effect occurred with light waves? Well, the higher frequency, when things are getting bunched up and they're moving toward you, the light's going to become more blue or violet. Remember, blue, indigo, violet. But I think typically what we observe is blue. And then if they're moving away, it's going to be red. So as the wavelengths are getting longer, it's going to shift red. So what we discovered is that pretty much all of the galaxies are actually red shifting away from us. That means that they are expanding outward, and as they're leaving a trail of light behind them, heading toward us, those light waves are getting longer and longer wavelengths. And so we are pretty much, it seems like everything in the universe is moving away from us, just about everything. And so there's a couple possible explanations for that. One of them is that Earth is actually at the center of the universe, and everything else is expanding out. God says, let there be light, and everything expands out from that point. Another possibility, and this is the more popular one, is that all of space is like a circle back in on itself. So if you traveled infinitely in one direction of space, and eventually you would end up circling back on the other, and that all of space is expanding out like a balloon. So you might be here, but all of space is expanding out. And so if there's another galaxy here, and another galaxy here, they're traveling away from you. So it turns out that if you believe this model, it's actually possible for a universe that's billions of light years across to only be thousands of years old if everything is actually spreading out, if the light is actually, if everything is red shifting out with us as the center. But if you believe this model, then the universe would pretty much have to be billions of years old for us to see some of the stars that we do. So anyway, we'll go over redshift in more detail in the next video. We'll also go over the parallax method for measuring distances. I kind of glossed over calculating the distances of stars in more detail and possibly hit a couple other things. So I will see you in the next video.